Well, thanks, Jim, for that introduction. It's a great honor to be giving the Sverdrup lecture, and it's really nice to see a lot of familiar faces out there. I guess I've been in this business a while. I know a lot of people. What I'm going to talk about is evaluating the ocean's biological pump. And so what I'm starting with this picture, this wonderful, beautiful picture of NASA ocean color. And in this talk, I'm going to show the correlation between how well you can predict the ocean's biological pump using this image or images like this, and the experimentally determined biological pump. Let's see. So I should be able to. So first of all, I want to tell you all what, it's a multidisciplinary audience, so I want to tell you what the biological pump is. This picture here on the left side is from the IPCC5, and probably in the back of the room you can't see this too well, but this part right here is the flux of carbon from the surface of the ocean to depth. And the numbers on there, if you can't see them, are 11 and 2, so about 13. That's what they say, and that's in petagrams per year. So the flux of carbon, the net flux of carbon from the surface ocean to the deep is on the order of 10 petagrams per year, as determined from a lot of different sources. And I've made a little blow-up of it over here, and what if you take a look at this photosynthesis equation, CO2 plus water gives you this. This is my interpretation of organic matter and oxygen. And the actual transport mechanisms are by particulate organic carbon, dissolved organic carbon, and some biological transport by species that migrate. In that order, probably the particulate organic carbon is the main one, maybe about 70%. I want to give a few little definitions so that when I say these things, you'll know what I'm talking about. Net primary production, NPP, is the amount of, that's what the satellite color is, or that's what it's supposed to be. It's the amount of carbon that's produced by plants. It's tuned with carbon-14 uptake experiments that have been going on for a very long time. I better be careful what I said because I just saw Dick Barber in the audience there. And then there is this net community production, Ncp, which is determined from metabolite mass balance. And they're not the same. Some of the carbon that's produced by plants is recycled by bacteria and by animals in the surface ocean, and the Ncp is the amount of carbon that actually escapes the euphotic zone and gets into the deep ocean. From a chemical point of view, this is what we want to know because this is what causes this is the metabolite that gets into the ocean and causes the chemistry change that we see in the deep sea. The relationship between Ncp and Npp is about 0.3. It's variable, but maybe not as variable as it was thought to be when Epley and Peterson defined it. But anyhow, it's on the order of, say, 0.2 to 0.5 or something like that. And there's one more term that I'm going to use a lot, and that's called ANCP, and it's just NCP with an A on it. That's the annual net community production. And over a year, the annual net community production has got to equal about the carbon export, the flux of carbon to the deep sea. So we'll talk a little bit about ANCP and the measurements of that. Why do we care about this? Well, there are a lot of reasons, and I'll just give you a couple of them. One is this is something that you've all seen a lot of times, I'm sure. This is the CO2 concentration in ice core, one of the most recent ice core, back to 800,000 years, and the CO2 waxed and waned by about a 30% or 100 ppm between glacial and interglacial times. And all the models that try to explain this invoke some combination of ocean circulation and the carbon and the net biological, the ANCP, or the carbon export. If the ocean didn't have any productivity at all. If it were dead, the PCO2 in the atmosphere would be about twice what the pre-industrial value was, about 280. So it would be something like 600. Different models give you different results. But I just gave that as a problem in one of my classes, and we got 600. And the other reason that I want to point out is that is illustrated by this map here. This is the oxygen concentration in the ocean at 400 meters. Here you can see the oxygen minimum zones. And if there are two long time series of oxygen at about 26.5 in the North Pacific and maybe 26.9 in the North Atlantic. These are the waters that are in the top of the thermocline that are just on the boundary between being ventilated and not being ventilated. And these long time series show that the oxygen concentration is decreasing, both in the North Pacific. These are 50-year time series. I think they're unique. I don't think there are any other long time series like this. And in the North Atlantic, this one's by Stendardo and Gruber, and this one was by Frank Whitney. And in both cases, they're decreasing by about a micromole per year, or maybe a half a micromole per year or so. Oops, something happened. I pushed the button. Got to go back. Wow. And the oxygen concentration in the deep ocean is a delicate balance between ocean circulation and the biological pump. So in order to is this decrease caused by some natural variability? Could well be, but it could also be because of global warming, who knows. But this is something that we need to work on, and that's an important topic for the future, I think. Now, if you Google the ocean's biological pump, you will find this picture here. And this, I think Penny Chisholm made this picture, and it was in a Nature paper. And I'm putting it here a lot of time. What a lot of people think of the biological pump are all these interactions between the phytoplankton and the zooplankton and the bacteria. And then there's this export term right here. This talk is just about the export term. I'm not going to talk about the ecology at all. There are a lot of smart people studying the ecology problem, and the answer is somewhere way off in the future, I think. But what I want to talk about, I'm going to keep it very simple. What I'd like to talk about is how well do we know this flux? So this is my talk outline. I'm going to talk about the biological pump from satellite observations and what we get from mass balance measurements and how they agree or disagree. I want to give two examples, or some examples from the ocean time series stations, which have been running since about 1988, because most everything is measured there at one time or another. And then I want to try to convince you that we can use oxygen mass balance to estimate the biological pump and what the evidence for that is. And I'm going to conclude that the satellite observations don't really agree very well with the measurements, at least in detail, and there are way too few measurements because they mostly come from time series stations. And the time series stations are really expensive, and we just can't do a lot more time series stations. So we're going to have to expand. In order to make progress here, we have to expand the number of time series measurements. You have to have a time series measurement because you need seasonality. And the only way to do that is on autonomous vehicles. I'd like to make some acknowledgments now. One of the great things about working in an oceanography department is there are a lot of people there who know a lot more about certain parts of the subject than you do. And I've taken advantage of that, I think. In everything that I talk about, or much of what I'm going to talk about, I've collaborated with three physical oceanographers, Steve Reiser, who is one of the Argo float persons, Charlie Erickson, who has developed a sea glider, and Megan Cronin, who is in charge of, who works at NOAA PMEL, and she puts surface moorings into the ocean. And The other great thing about working at a university is you have great graduate students, and I just want to acknowledge 4 of them here. Seth Bushinsky has done a lot of work. He's my student, and much of what I talk about toward the end will be his work. Noel Pellin is a student of Charlie Erickson, and he's been studying oxygen on sea gliders. We're going to see some data of his. And former students David Nicholson, now at Hui, and Roberta Hom at UVic also studied this project. I'd like to acknowledge the researchers whose work I'm going to quote in the talk, and funding from NSF. Okay, so let's start on this. These are 2 pictures, recent pictures of the satellite-determined organic carbon export. And that involves evaluating the net primary production from satellite color, and then you have to also apply this Ncp to net primary production ratio. That ratio that I said was 0.3. It's not just 0.3. It varies from different places in the ocean. And these fluxes that I'm going to talk about here are in moles carbon per meter squared per year. That's going to come up over and over, so you can just kind of figure that unit. And this is from Davey Siegel's paper in 2014 and from Toby Westbury in 2012. And I just want to draw out one thing to your attention. One, it is that the variability here between the oligotrophic oceans and both the equator and the high latitudes is pretty big. I mean, the oligotrophic oceans in both of these completely different, well, they're not completely different. They use the same satellite data. But this one uses an ecosystem model and this one does not. Is the variability in the carbon export is something around in the oligotrophic oceans about 1/2. And in the equator and in the high latitudes, maybe up around 3 or 4. So maybe a very clear 3, 4, 5 time variability in the carbon export as determined by these values. And I think in both cases, the flux is on the order of 10 petagrams, the same as what that IPCC picture that I showed at the beginning came up with. And this is this I'm showing because it's a model-derived organic carbon export, and this is from Moore et al. In 2004. 2002. There are a lot of other ones, more recent ones. And the point here is you see the same thing. The oligotrophic oceans, the carbon flux is maybe 1/2 in the oligotrophic regions, and in the higher latitudes and at the equator, it's up around 3 or 4. Now, if you take a look at the places where we've measured this flux by mass balance, and again, there are only about 4 or 5 places in the whole ocean where this has been done because you need a time series station in order to capture the seasonality. And this comes from a paper that I wrote recently, and it kind of summarizes these at the time series stations and at the equator. The equator really isn't a time series station, but it's not very seasonal, so I included it. And if you take a look at these numbers, they're 2.3, 2.5, 3.3, 2.8, 3.8. So the ANCP, the carbon export, is 3 plus or minus 5. It doesn't vary by a factor of 4 or 5 in the ocean. Well, do I really think it's 3 and not geographically variable? No, I don't. But so one of the things, but we have a problem, right? I mean, this wonderful resource, the ocean, the NASA's ocean color is telling us one thing about the biological pump, and the experiments that we have made don't indicate a lot less variability. This is another way to approach the carbon export. This is from a paper by Rolf Sunnerup in 2013. And what Rolf did is he measured the OUR, that is the oxygen utilization rate below the euphotic zone. So if you know the age of the water since it outcropped, and you know the change in the oxygen concentration from the outcrop to where you make the measurements, or the AOU, then you can determine the oxygen, the OUR, the oxygen utilization rate, and then you can integrate that as a function of depth. And that, since most of the carbon is oxidized in the top 200 or 300 meters of the net respiration zone in the ocean, that has to equal the carbon flux out. And so Rolf has done this in the North Pacific from Station P down to Hawaii, right there along that transect. This is the SF6 data. He determined the age of the water mass. By the age, I mean the time since it outcropped, when it was at the surface where it got its oxygen saturation value. He used SF6 to determine that in a lot of modeling. And from the SF6 and the AOU data, you get these values right here. So there's 3, and it gets, here's the equator, or 20 degrees, and there's Station Papa at 50 degrees. And if anything, it might go up a little bit. If anything, it decreases from the low latitude into the subarctic, from the subtropical into the subarctic. Just the opposite of what the satellite is telling you. So this looks a little bit like what the surface ocean measurements are telling us. Okay, now a little bit of a couple of lessons from the ocean time series sites. Not too long, just a little bit. What I'm showing here there are 3 time series sites that I'm going to, there are more than that, but the 3 ones that I have summarized here are the Hawaii Ocean Time Series, the Bermuda Ocean Time Series, the 2 American time series, and the Canadian Station P right here at 50 degrees north. And these symbols here, now this is the Ncp, you can't see the numbers very well there. There's 2, 3, 4. These symbols are the mass balance determined carbon export. They're determined not just by oxygen mass balance, they're determined by dissolved inorganic carbon mass balance, carbon isotope mass balance, nitrate drawdown, so all kinds of different kinds of mass balance. They give you about the same story, something like 3 plus or minus 1. 3 plus or minus 1 is a good number. These are the sediment trap fluxes. At all of these locations, sediment trap fluxes have been determined in very great detail, and you can see that they're a lot lower. And there are a couple of reasons for this. Part of it is because the particle flux is only one of the mechanisms of carbon escaping the surface ocean, and part of it is probably because the sediment trap fluxes are not very accurate. I think that Ken Bissler and others have shown that that's true. So then if we do one more thing with this data, if we take a look at how well it is reproduced using the satellite measurements, anybody can do this. You can go to the Oregon State website, and the net primary production is given on that website in the whole ocean, and as a function of time. So I just cut out little spots around the time series sites. And so these are the 3 different time series sites, and the symbols again indicate the mass balance determined carbon export. So let's start here at HOT in the subtropical Pacific. The red symbols there are mass balance determined carbon export, 4 different times. This one is kind of low. That's Roberta Haum's thesis right there. And there are 2 different satellite determined exports here. There are 2 different versions. One is the original Barenfeld and Falkowski method, where they just utilize ocean color to determine the net primary production. And the more recent one by Westbury and Barenfeld, in which they use satellite color and optical backscatter. They think they can determine the particulate carbon content from optical backscatter. And you can see that at HOT, the original one was too low, but the new one is, it's up around 3. That's a big improvement. And if you take a look at Ocean Station P in the subarctic Pacific, you get the improvement there too, but it's in the opposite sense, that the old one, the original Barenfeld and Falkowski, gave too big of a carbon export, and now with the newer version, it's certainly within the error of what we measure by mass balance. At Bermuda Atlantic time series, nothing works. The carbon export determined from carbon oxygen, not oxygen only, but DIC, carbon isotopes, and oxygen mass balance is a lot higher than the satellite determined value. So some progress is being made. It's not like these things don't work at all. The newer version of the satellite determined productivity seems to work better. I think that I should say, though, that there's a recent paper by Lori Juranic in which she summarized all the net primary production as determined from the 017 data, and maybe something like 10 places in the ocean, 5 to 10 places in the ocean, and did the same comparison. And she finds that the ocean chemistry, the mass balance determined primary production in every case is quite a bit higher than the satellite determined values. So maybe it's not as optimistic as what I've got here. Oh, yes. Now okay, it's intermission time. You've all, it's almost lunchtime and everybody's getting a little nervous. This is not a selfie. It's not a selfie of you wondering if you're going to get that NSF proposal funded. That's not what this is. It's just an intermission. So are you going to tell me when I have about 10 minutes left?
Yeah, you're doing fine.
Okay. Jim just told me there's nothing following this, so we're going to be here for several hours. Okay. So now I want to talk about the third topic, and that is I want to convince you that we can determine the carbon export using oxygen mass balance in the upper ocean. And I've come back to my little picture here. And as you recall, CO2 plus water gives you organic matter plus oxygen. And so for every, and we know the stoichiometry of this organic matter to oxygen production pretty well. It's 1.45. I mean, I'm sure it must be variable, and we haven't discovered that yet. But you know, it seems to work out pretty well in lots of different cases. So it's probably not bad. So if we can determine, if we want to determine, since we can't determine the carbon flux out very well, there aren't very many good ways of making that measurement. If we can do a mass balance on the oxygen, and by doing that, we have to know two things. We have to know that mainly the oxygen transport into the atmosphere, and there is also some oxygen transport into the upper ocean. But if we can do that mass balance, then we can take that oxygen, the net biological oxygen production, divided by 1.45, and we get the carbon export out. And this has been done a bunch of times, and I'm going to review just a little bit about that before I go on to how to maybe do this in a lot more places in the ocean. And I think that the person who really has to get a lot of credit for this is Jenkins and Goldman. Back in 1985, they took the Bermuda, or maybe it was Station S data, maybe it was Panularis data, something over there around Bermuda. And they, and Bill and Joel Goldman used an oxygen mass balance. They made a model, and they determined that the net biological oxygen production was quite a bit higher than most biological oceanographers thought it was, or thought it should be. And that kind of started this whole business. It's been done by Roberta Hamann, myself, and Rachel Stanley recently did the same thing at the BATS time series station. There are measurements also of oxygen on autonomous platforms, surface mooring, ships of opportunity, sea gliders, and profiling floats, and I'm going to talk a little bit about that. This is a picture of the oxygen concentration on a surface mooring in two places in the ocean. One is this Hawaii Ocean Time Series, and one is up there at Station P. And one of the main reasons I'm showing you this is I want to impress upon you that in order to be able to determine the oxygen flux to the atmosphere, which is what I'm trying to get at here, you have to be pretty good. You have to make good measurements. This is the oxygen concentration. The units here are supersaturation. So 0 is exactly what you'd expect the oxygen to be if it were in equilibrium with the atmosphere. And you can see at hot, it maybe gets up to 2% supersaturation, and there's not a huge amount of seasonality. What I'm showing on here also is the nitrogen concentration, and nitrogen gas, that is. And we use nitrogen gas as an inert tracer because we can measure it on a mooring. And so the difference there is between the biological signal, roughly speaking, not exactly. But that difference is the biological signal. And so we're trying to make a measurement of about 2%. So if, did it again. We're trying to make a measurement that is about 2%. And the chemists would say if you want to make a 2% measurement, you have to be able to you have to have accuracy to, 0.5% at least, a couple tenths of a percent would be nice. So in order to do this remotely, we have to be able to make oxygen measurements to better than 0.5%, I think. You can do that on a mooring because we can calibrate these at these time series sites. We can go calibrate them with Winkler titration, and we know what the sensor is telling you. This is the data at Station P, and you can see there's a lot more seasonal. There's a much bigger difference in the summertime. Well, it's 4%. And in the wintertime, the nitrogen and oxygen fall pretty much on top of each other. So you really can't distinguish any net biological oxygen production there. This is some data that, from a paper that Paul Quay published in 2011. And it is an interpretation of oxygen from the Cronin data set. And most of these oxygen measurements were measured on ships of opportunity, and that's why I have it here. So you put an oxygen sensor in the hold of a container ship that goes between the United States and Europe, back and forth. You do it from 1990 to 2005. You have a lot of surface ocean measurements, and you get the seasonality because it goes back and forth a lot. And what you see is that the oxygen in the North Atlantic here, the oxygen supersaturation in the wintertime is about 5%, and in the summertime it's undersaturated. So that's why you have to have the seasonality. The carbon that escapes the surface ocean is represented by the oxygen represents the carbon that the oxygen over the whole season, the integral over the whole season, is the number you want, because that tells you how much carbon has escaped the euphotic zone, or the depth of the winter mix layer. Okay, there are about more than 3,000 profiling floats in the ocean, and I don't have them all on there. You can get another picture that shows those. And something like 250 have oxygen sensors, and that's what I'm showing here. So if you can make oxygen measurements on profiling floats, and if you can do it accurately, then presumably you can put some floats in the North Atlantic and some floats in the South Pacific and places like that, and do an oxygen mass balance and calibrate the satellite picture. The problem is none of the oxygen sensors on these floats are very accurate. There has been an attempt to calibrate them in the literature, and you can do it to plus or minus 3% or so, according to the Takashita et al. Well, plus or minus 3% or so is not good enough, right? So, and I want to acknowledge this paper by Johnson, Reiser, and Carl, in which they showed the oxygen. This is the oxygen anomaly. It's the difference between the saturation value and the undersaturation value. The warm colors are positive. There's the subsurface oxygen maximum. Here's the winter. Here's the summer. This is from, in Ken Johnson's paper, this is from oxygen on profiling floats. These oxygen sensors, put in at the Ocean Time Series station hot, these oxygen sensors were calibrated against Winkler titrations when they were put in the ocean. So that's pretty accurate. But we got to get away from the time series station, right? I mean, most of Argo floats are put into the ocean on a ship of opportunity. They stop the ship and they throw it. They don't throw it. They lower it over the side. Sometimes they throw it, I guess. Do they throw it? No. Lynn says you do not throw them. So, we have attempted to fix this, and this is Seth Bushinsky's PhD thesis work. And what we did is a couple of years ago is we had a student cruise over there by the Kuroshio extension, and before that we put one of these beasts into the around Ocean Station P just as a test case. So what we've done is we put the oxygen sensors. This is real brilliant, right? You put the oxygen sensor on a stick. This is just a sensor on a stick. Normally the oxygen sensor is down here. We put it up here. These oxygen sensors are Andera oxygen sensors. They're good things, but they drift. And what we do is that, this is in collaboration with Steve Reiser, what we do is when the Argo float comes to the surface, we don't turn them off. They come to the surface to send the data back home. We leave them on. And so the optode, what is called an optode, this oxygen sensor determines the oxygen content of the atmosphere, and you all know that the oxygen content of the atmosphere is everywhere about the same. We have to worry about moisture because the PO2 is what does, the mole fraction is what doesn't change. So if it's not 100% saturated, we have to make a correction for that. So these are the results at, this one at Station P has been in for a couple of years, so 2012 to 2014. This is the result from the upper one. Now this is the oxygen, this is, the units here are the percent difference from the atmosphere. So we calibrated this one by this measurement right here. We put it into the water, made the measurement in the atmosphere, and calibrated the sensor to that value. We also, when we did this, we did a Winkler titration calibration and got the same result. And you can see that over a period of 2 years, it's pretty stable, but it's drifting down. And it's drifting down by about, maybe 1% or 0.5% after 2 years. So that's pretty slow drift. But if you didn't calibrate it, these things stay in the ocean for about 5 years. So if you didn't calibrate it, by the end of 5 years, you would be measuring something like 2% too low. And remember, the signal that we're looking for is on the order of 2%. So in order to use these to determine the oxygen flux, I think you have to calibrate them in situ. The lower one, this one is much more variable, and we think that the reason for this is that it's being splashed by oxygen supersaturated water in the summertime and oxygen undersaturated water in the wintertime. And it may be more complicated than that. I don't know. But anyhow, that you would, from this data, you would say that if you're going to do this, you need to have this oxygen sensor significantly above the ocean so that it doesn't get compromised. There may be other ways of using data like this to back out the real signal. That's possible. So one more slide about that. This is the oxygen, this is the supersaturation in the surface ocean from that mooring at Station P, 2 years here, no, just 1 year. Almost 2 years. And the black line is also from an oxygen sensor on the mooring, Megan Cronin's mooring there, that oxygen sensor is calibrated 3 times a year. So we go, the Canadians go there, we go there, and we calibrate the oxygen sensor using Winkler titrations. And during this period, it drifted down by about 3%. So they tend to drift more in the surface ocean than they do if they're stored deep in the ocean, for reasons we don't know, understand. The other value, the red ones, is the oxygen sensor calibrated using the surface calibration. And I think you can see that I can convince you that those two agree pretty well. So I think we're making some progress so that we can actually make the measurement as well enough to do what we would like to do, which is the oxygen mass balance. And I want to show you some, I have made a movie for you. I didn't make it. People in the audio visual place made it. This is a movie of oxygen supersaturation in the ocean at Ocean Station P. I'm going to show data from a glider deployment here. This square is about 50 kilometers, and Argo float data that I just showed you. This square is about 250 kilometers. We're going to see data from the top 200 meters of the ocean only, and this is then the float data, the Argo float data. This is, the colors are, this is percent supersaturation. So the colors are blue. Blue is undersaturated. Red, the warmer colors are supersaturated. Yellow is very supersaturated, up around, say, 6 or 8%. What's going on down here is that is a picture of the surface value, the very surface oxygen supersaturation as a function of time. So it's in the wintertime now, and this little white thing that you see going there, that line is the mixed layer depth. So the mixed layer is deep, and the float is surfacing about once a week, and it's coming into the summer, and there you can see the mixed layer shoal. It gets a little bit red. There it gets more red. The oxygen concentration in the surface ocean is becoming higher. And now you can see, pretty soon you'll see the characteristic subsurface oxygen maximum right there, that yellow thing right there. That's because oxygen is being produced by biological processes underneath the mixed layer and it can't get out. But the most important thing in terms of the mass balance is the surface supersaturation. Now we're going into the wintertime again, and it's heading back there. And you can see that the mixed layer depth has gotten a lot deeper. And it's going to go back and hide here among these trees back here. It will be hard to see, but we'll be able to see a little bit as the supersaturation starts increasing. There you can see it. There you can see the last summer. That's of 2014. So this is the kind of data you get from a float with an oxygen sensor on it. This is a glider. This work was done in collaboration with Charlie Erickson, and we put the glider in a butterfly pattern. Same story, same colors. The same thing is going on here, except here you see one of Charlie's pink gliders rather than a float. And it looks like it's happening a lot faster, but the glider just makes a lot more profiles. It takes about 2 weeks for the glider to do one of these butterflies, and during that period you get something like, you get 2 or 3 profiles every day. And it dives to 1,000 meters, so you can't, if you look very closely, you can see that these are little inverted V's. It dives to 1,000 meters and then back, but we're just looking at the top 200 meters because that's where the important oxygen signal is. And it's in wintertime, so it's very blue now, and we're going to come up into the summertime here, and we'll see that the surface, we'll see that the mixed layer will shoal, and the surface oxygen concentration will start getting red. There it starts coming, right there. That's when we changed gliders in June. So we got supersaturations of up about around 5%, and you can see the kind of detail that you can get using an instrument like this in a virtual mooring. Okay, this is about over, but so I hope that I've convinced you that we can make this measurement remotely, and that we can just now probably make it accurately enough to determine the air-water exchange rate. But that's just the beginning. I mean, that's fundamental, right? You have to get the measurement right in order to be able to interpret it. You can always interpret it. The models will always improve, and you can always do a better job of interpretation. But the way that we do this right now is we have an upper ocean model, and I'm pretty much near the end. This is not going to take very long. How much time do I have? So this is a kind of a depth coordinate, and this is a time step of the model. The model has a mixed layer and layers below it, down to 50 depths, down to 150 meters. The change in oxygen concentration with respect to time is equal to the air-water flux, that's the blue arrows here, the entrainment value, that's these green ups and downs, advection, horizontal advection determined by climatological oxygen distributions and geostrophic flow and Ekman transport, and this diffusion, that's this F sub D, and that's the exchange between the mixed layer and the value below. If we can evaluate all of these things, then we can determine this term right here, which is the net biological oxygen production. So that's what we're after, but in order to do that, we have to evaluate these. The main terms, I'm not going to spend a lot of time on this, but the main terms are the diffusive gas exchange and the diapicnal diffusion. The other ones are pretty small. Entrainment and shoaling is not small, but you measure the temperature and salinity on the float, so you can tell how the mixed layer is moving up and down. So gas exchange is kind of the dominant process, and I show this one just to show you that this is an interpretation of the nitrogen data at that mooring using the gas exchange model of Liang et al. This is the model that we use. And the data from this GTD at gas tension device at Station Papa are the red, and the model-derived values are in blue. Liang has made this model in which the gas exchange, both the air-water exchange and the bubble processes, are a function of wind speed. So the only thing you need to know is the wind speed. And you can, and I just wanted to convince you that I think that we can determine the air-water exchange rate. This is on an inert tracer, this is on the nitrogen. We can, to indicate, so that we test the model using the nitrogen gas, and I think we can do that pretty well. So this is about the end. This is a section of oxygen supersaturation from that one mooring that I've been showing you. This is the model result in terms of cumulative flux. Here's these units, moles per meter squared, so by the time you get to 1 year, you know what the biological production is. This is the flux at the air-water interface, the big term, the blue one. The change with time, the measured change with time on the float is the DO2 dt is this gray line. And the other important term, this flux at the base of the mixed layer, is this red value. And that one's hard to determine. That's probably going to give us the most trouble. It is estimated, in order to determine this, you need an eddy diffusion coefficient to determine the flux, and a gradient. The gradient's okay, but it's hard to do the eddy diffusion coefficient. We're using values that were determined by Megan Cronin on a heat balance there at Station P. And the important thing to note is that the N value it's not very far from 0. It's between 0 and 1. So I think that my first efforts, remember I had a value of around 2 moles per meter squared per year. My first efforts were probably wrong. I probably didn't get the wintertime right. If you include the wintertime, so you've got this net biological oxygen production in the summer, but in the wintertime, two things happen. One, there might be net heterotrophy, it might be net respiration, and you're also bringing up low oxygen from the top of the thermocline. And that pretty much wipes out the signal. So I would say that this agrees, if you remember, pretty well with what that Rolf Sunnerup latitudinal dependent biological oxygen production was. It actually decreased toward the high latitude. And we're finding that our estimates probably decrease as well. Maybe it's between 0 and 1. This is the first cut at this modeling, and it may evolve a little bit yet. Okay, so these are my conclusions. So the geographic distribution of the biological pump determined from satellites is probably too variable. The experimental results that we have so far would indicate that. I think that the net biological pump can be determined from annual metabolite mass balance measurements, of which one is oxygen. I think that the calibration of the in situ determined biological pump requires a global distributions of Ncp measurements. We can't really calibrate it yet. You can't calibrate a global signal with 5 measurements spread around in the ocean. You need a lot. And we're not going to get any more time series stations because it's too expensive. You all can probably deal with that. So it has to be done remotely, and I think that we can do this by making in situ oxygen measurements now, because we can get accurate results. It's just got to go do it.
We do have time for a question or two. Steve, you want to?
I'm not a conclusion scientist. I'm wondering how this relates to pH change in the ocean. This looks like it might almost be emerging.
Repeat your question.
pH is changing.
She wants to know how this is related to pH changes. Well, pH change is caused by anthropogenic CO2. The ocean acidification is what I assume you're talking about. How does it relate? You could see a diurnal pH change, and I think Ken Johnson has developed a pH sensor that goes on Argo floats.
Just put out our
12th one.
2 days ago.
So there are ways of actually monitoring that using the same kind of remote sensing. Dick. Well, Dick, I showed some annual satellite data, and those were the satellite data from the time when my measurements were made, and you can see that the satellite data doesn't change a lot. There's not a big seasonality. Well, there is a seasonality. There's not a big seasonality in the. Oh no, sorry. Those were annual averages from the satellite measurements. And I did the averaging myself. So you can see the seasonality from the satellite measurements, and I made the annual averages. So satellite is average as well.
Yeah, but Jenkins, it wasn't an average. It was a process that was average. And the satellite data is instantaneous. It has no memory.
So Dick is saying that the time scale of the measurements are different. The satellite is an instantaneous measurement, and the oxygen mass balance is not. And the oxygen mass balance is modulated by the residence time of oxygen in the surface ocean. That's true. So there's a mismatch there to some extent.
Steve, in the wintertime, in a lot of the data, you show undersaturation, which really imply no carbon flux. The traps always get something.
Great.
So where's the flux coming from in the winter?
That is the question. I mean, so we're showing net heterotrophy right now and the oxygen mass balance in the wintertime. And C.S. Wong had sediment traps out there for a long time, and the carbon flux in the summertime is a lot bigger. It's like 5 or 6 times bigger, but there is something in the wintertime. So I don't know. It could. I mean, you can think of possibilities like a seasonal change in the DOC standing crop might be what's overwhelming or determining the oxygen mass balance, and you can still get some particle flux out. But that's a great question, and I don't know the answer to it.
Okay, I think we need to end then, so let's all give Steve a great hand for this.